Welcome to the review for quiz number 11. And this is on Laplace transforms. Inverse Laplace transform, sorry. The Laplace transforms is kind of not so hard, right? So in the inverse Laplace transform, you're allowed to use the tables, although there is not much of the table we use. It's always the same thing, so I don't see really the point in that, but okay. If you feel like using the tables, you're allowed to do that. But as I said, you can use the book anyway, so for the quizzes. Okay, so let's dive into it. So here's, we'll do a couple of examples. 2s cubed plus 2s squared minus 12s plus 6 over s times s minus 1 times s plus 1 times s minus 2. So what is so nice to factor the denominator, if you would expand this, it would be much harder to find the factorization. Factoring is not easy at all. In fact, it is a hard problem. In the technical sense, if you take discrete math is our problems considered to be intractable in general. Okay, so, but we are lucky, we have this factored. But for the inverse transform, which is basically a practice of partial fractions, we need a partial fraction. Because in the table, you're never going to find anything of this form. Okay? You do find reciprocals, 1 over s minus 1, and so on, those you find, but not this combination, but the partial fraction will resolve this. So we know that the partial fraction will be of the form as plus b s minus 1 plus c s plus 1 plus d s minus 2, and then we have to find this a, b, c, and d. Now, the good thing is these are all distinct roots. And in this case, and only in this case, we can use the so-called Heaviside method to calculate them. And so how does this method work? Well, you take your fraction, 2s cubed, plus 2s squared minus 12s plus 6 divided by s minus 1, s plus 1, s minus 2. And to calculate, say, a, let's start with a, what you do is you scratch out the factor, that the denominator that comes to a, that is s, and then plug in s equals 0. And that gives me 6 over minus 1 plus times, so minus 1 times 1 times minus 2. So I get 6 divided by minus 2, that is 3. And that gives me a. So I'm going to, this is a video, right? I can do this. So I'm going to replace a now by 3 and then use the same. But you have to write this out, right? I'm sorry, but I need to see all the details. So on the quiz, I need to see all the details, including, if you use Heaviside, each calculation of Heaviside. That is, for me, the only way to check. It might be, you say, this is like, why do we need to show everything? Well, you need to do it, right? And so if you do it, why don't you show it to me? And because if you don't do it, yet you present me with a solution, then I can only assume, well, you got it from somewhere else, illegitimately. Okay? All right, so b, I do the same thing. b is on top of s minus 1, so s minus 1 goes, and I plug in s equal 1. Okay, then on top I get 2 plus 2 minus 12 plus 6. Then in the bottom I get 1 times 2 times minus 1. So that would be, that we do it in black, 4, 10, so minus 2 over minus 2, I get 1. All right, so b is 1, and again, oh, there's my 1, that came out nice. These calculations go. And we do c. This time c is on top of s plus 1, so it's the s plus 1 that I'm going to cancel out. And plug in, what do I plug in now? S equals negative 1, right? It's exactly the one that makes the factor that I cancels out 0. Okay, if I plug in negative 1, negative powers, odd powers are negative, odd positive powers are positive. So I get a minus 2, plus 12, plus 6, and in the bottom I get minus 1, minus 2, minus 3. So on top this is 18, and in the bottom I get minus is minus 6, so the whole thing is minus 3. Okay. So this is minus 3. And then I can get rid of everything. And finally find D. So this time s minus 2 is cancelled, and I plug in s equals 2. So on top I will get 8 times 2, that's 16, plus 4 times 2, that's 8, minus 24, plus 6. In the bottom I get 2 times 1 times 3. So the top is 24 minus 24, so that's 6, and in the bottom I get 2 times 3, that's also 6, so actually I get 1. Okay, so that's the last one. D is 1. Now, this is the first part, is the partial fraction part, so this is, if you want, step 1. Now, of course, we have to write down the inverse Laplace. And we know that powers of t corresponds to the reciprocals of s, but with 1 power higher and with an n factorial that comes here. So there's an n factorial as an extra thing here. Now, in the simplest case, this means that 1 corresponds to 1 over s, and that's the case that we are in with a single root. With the multiplicity 1. If all the roots are distinct, then this is the rule that we're going to use. But of course, we also have shifts. So we also plus the shift theorem. So I remind you that what does that do is multiplying with e to the at corresponds to shift s, replace s by s minus a. Okay, so now it's the opposite, right? So we going in this direction. So if we have a shift by s minus a, then we have to multiply with EAT. Okay, so the very first one, there is no shift, so we get the inverse Laplace. So the inverse Laplace, let me just spell it out, is equal to, well, there is no inverse, no shift, so it is just 3. Then the next one, the coefficient is 1, but there is a shift by 1, so that would be ET, right? It is, yeah, s minus a corresponds to e to the power at, so be careful with the signs here. Minus 3 times, now the shift is with negative 1, right? So now it's e to the minus t, and then plus e to the minus 2t. Now we have 2t, right? S minus 2 corresponds to e 2t. Okay, so that's the function. Okay, we don't have to write this one here. That is the function, the inverse Laplace transform in this case. Okay, that's the case where we have no multiple roots. There's another case where we have mixture, and I'm going to do a little bit of extreme case. Let's look at this case here. S squared plus 5s plus 10 over s plus 1 cube. So we know that is of the form as plus 1 plus bs plus 1 squared plus cs plus 1 cube. Remember, this power tells you the multiplicity, and you have to put in not only that highest power, this one, but all the ones before that, until you hit the first power. So in this case, we have 3 of those guys. Now, we can try to do A, B, C with which method? We cannot use Heaviside because these are multiple roots. That's exactly what is not allowed there. And we can use the general technique that we'll see in the next example. But in this case, there is a shortcut. And so the shortcut is write as a polynomial in s plus 1. because the denominator is s plus 1, so we're going to write the top also as polynomial s plus 1. Only in a special case where we have a single power. If we would have some more stuff here, then this doesn't work. Well, it does work, but it's not going to make life easier. You can do some things, but it's still going to be messy. So only in this special case you can do the polynomial in s plus 1. Now there's a technique that we have to do many more times. So we are kind of used to this now. So we write, that means we're going to write s plus 1, take it in, keep it together, minus 1. So this would be s plus 1 minus 1 squared plus 5 s plus 1 minus 1 plus 10. So I'm working on the numerator. Notice I'm not trying to factor the numerator. That is completely useless. Do not factor there, right? I'm not trying to factor. What I'm trying to do is write it as a polynomial in s plus 1. So then this I expand. This is s plus 1 squared minus 2 times s plus 1 plus 5 times s plus 1 minus 5 plus 10. So what we have, that is s plus 1 squared minus 2 plus 5, that is plus 3 times s plus 1. And then we have 1, 11 minus 5 is 6. So this is what the numerator looks like. And then the denominator is s plus 1 cubed. So once you have done this, the next thing is now we divide out. That means we're going to divide each term by s plus 1, and we're going to have reciprocals, but that's okay. So we get 1 over s plus 1 here, because all the other powers, there are 2 on top, 3 in the bottom, so 1 in the bottom left. In the second, for the second term, for this term, I get 3 over s plus 1 square. I hope you see that, right? One of the powers cancelled. And then the last one, okay, I have everything, x plus 1 cubed. And this is exactly of the form that we predicted it will be. Okay, but to find 1, 3, and 6 from this method would be cumbersome. It would take some while. Okay, not extremely long, but this is, I think, quicker. And also, the quicker the methods are, sometimes the less prone to errors they are. But okay, so what do we do now? We go back to here to our little table, if you want. Powers correspond to reciprocals. Of course, we're going to think this way, right? It's an inverse Laplace transform, so we know that reciprocals correspond to powers of t. Now, which reciprocals do we have? We have a first, degree 2, and a degree 3. So this will correspond to, in t, either if you take the inverse Laplace, so let me do the inverse Laplace here, so L inverse, what will that do? Well, in the first one, I will get no power. Here, I'll get a power 1, and here we'll get power 2. Okay, so we know already the powers, and also we know the coefficients, so there will be a 3, and there will be a 6. But what is still missing here is that it's not really, so t to the power 1, of course we don't write, so we get just 3t, so, okay, so this is what we get. It's not complete yet, because this would be if this would be just s in the bottom, then we would get this one. But there's a shift, and the shift is, so here a is negative 1, right? It is always s minus a, and that the shift is obtained by multiplying this with e to the minus t, and each term. So you don't have to write it 3 times separately, right? It's each term multiplied with e minus t. So that's the solution. Right? We write it a bit nicer. I'll write it in blue, since everything is in blue. So e to the minus t times this term. That's the inverse Laplace transform of this very special form of a multiple root. And now I'll do one where we have no other recourse than actually work out the method of partial fractions in its long form. So that is 3s squared plus 8s plus 64 over s minus 1 times s squared plus 6s plus 8. Okay. Now, it's already factored, and there is no way that you can factor the bottom one more. Sorry, not 8, 18. Plus 18. The quadratic formula, if you do the discriminant, you see immediately that this gives you zero, negative discriminant. So should I use it? Can we use a quadratic formula? No, the quadratic formula is useless here. We find the roots, but the roots are complex numbers and we cannot use that. So although there are roots, we cannot use them. Okay, if you think complex numbers, because we want to keep everything real. This is what is called real analysis, differential equations. So what we need to do? Well, this is, so since it's a quadratic irreducible, so we have a quadratic irreducible, the first step, so I'll write it here, step 1, is to actually complete the square. And this is something we need to do now, not later, because we need to know what so-called, how do we center this thing, okay? We know that this is going to be of the following form. A over s minus 1 plus, and in the second fraction we'll have this in the denominator, and on top we will have here a linear polynomial. But if I write bt plus c, then later on, bs plus t, later on I will have problems finding the inverse Laplace. So I don't need the, it is a linear polynomial, but in the variable, in the variable if you want, or in the twist, given by the completed square. So that's why I need to complete the square here, because at the moment I don't know yet what this linear form should be. I know it has indeterminate coefficients, but what is the variable? Okay, so complete the square. So to complete the square, I remind you, you keep the two s terms together, write the third term a little bit further. Here you divide this by 2, this gives 3, and then you square this and you put it there. Now once you do that, you added 9, you have to subtract the same 9. Okay, so this is the complete new square. For simple, the simple case here is because there's the coefficient is 1. But since we're only looking at those cases, I don't want you to, I'm not going to review the more general method. If you don't understand or not know anymore what this works, look it up, okay? So what does this now mean? Well, this means the first 3 terms now is a double product, is a perfect square, is s3 squared, the 3 is being this 3, and this one, of course, is just 9. Okay, so we have the form that we want. I'm going to just now be lazy and replace it. It's going to be s plus 3 squared plus 9. Now, do we have to do something with the 9? At the moment, not yet. That's not a concern now. But we now know how the linear form on the top will look like. It will be a polynomial in s plus 3. So it would be b times s plus 3 plus c, or whatever letters you like. If you like other letters, you can use other letters here, right? As long as you don't use the same letter twice. Okay, so that's the form that we want to find, but it still requires us to find it. And so the steps now, step 2 is now to multiply everything out. So on the left-hand side, I'm just going to get the numerator. And on the right-hand side, we have to be careful, right? So we're going to multiply this everything with this product. So if I multiply it here, it all cancels out. If I multiply here, the s minus 1's cancelled out, so the other guy stays. Now, it is advisable to write it in this form already. You'll see why. Okay, and then in this, if I multiply this fraction with this whole denominator, of course, these two guys cancel, this and this cancel, so there's an s minus 1 left. Okay, perhaps I should write it here because I don't know whether, otherwise people get confused. S squared plus 6s plus 18. So here we multiply with s minus 1 times s plus 3 squared plus 9, and here we multiply with s minus 1 s plus 3 squared plus 9. So here these two cancel, and here these two cancels, okay? So what we have left is the bs plus 3c times s minus 1. Now be careful, it's this whole thing, the whole numerator. So it is b s plus 3 plus c between parentheses, multiply with s minus 1 also between parentheses. Because we will not expand this, but it is a product of two sums, so we have to have parentheses there. Okay, so that is the step 3 now, is we're going to plug in values. Plug in values for s. And there are the first choice is roots. So that's the first one we're going to try to find, roots. Now there's only one, and that is s equals, what is root here, -3? No. We're talking about roots of this denominator, so this is s equals 1. So s equals 1. What is the result of that? Well, the result of that is that this term disappears. So don't expand it, because otherwise it takes you a lot of calculation to see that the whole thing is gone. But here, this of course doesn't vanish, and of course neither does the left-hand side. So I get 3 plus 8 plus 64 equals a times 1 plus 3, that's 4, squared is 16, plus 9 is 25. And what is this guy? That is 75? 72, 75, yeah. Oh, okay, a is 3. So that comes easy. Roots always gives you at least one of the constants. Now the second one that you want to look for is the center, if you can. If the center happens to be the root, bad luck. I might ask that. So don't get angry with me if I ask you to do that. Then you have to solve a system of equations. That is a little bit more work, but we have done this several times. So it's not that this is the first time, oh my God, I don't know how to solve a system of equations with two unknowns. We have done it from almost the first term onwards when we were looking for, well, we have done this many times in this course. So the center, what I mean, the center of the quadratic irreducible, that's what I mean. And what is that here? That is -3. Right? That is, remember this is s minus -3, right? So, or if you want, what makes this 0? Namely s equal to -3. Okay, we plug in both sides again. That is 18 minus 24 plus 64 is equal to, now what is the advantage? That s plus 3's cancel. So we have 9a, there's no b, this part is cancels. And then we have c times -3 minus 1, that is -4. Now we know that a is 3, so this is 27. Minus 4c. So what does this all give me? So that is 82. No, this is, let's do it this way. -6, so this is 58. And then the 27 to the other side. So this, or perhaps, no, switch it the other around. So 4c is equal to 27 minus 58. That is 31 minus 31. Sorry, I just want to see why. I thought it was nicely divisible, so I don't know whether, did I, was 18, oh, 18s, sorry, I copied, no, 8s, no, I copied it right from my notes, so what did I do wrong then? Because that is correct, right? Yeah, that is correct, so let me see, I plug in -3, if I plug in -3 here, here this is 9 times 3. Oh, 9 times 3 is 27. Oh, okay. I always try to get round numbers. Now, I cannot promise you, and so just because your numbers are not round, you should say, oh, I'm wrong. Okay, so this becomes now minus 24. This is 40. The 27's cancel, right? Sorry, yeah. So this 27 is also here. Plus 40, the 27's cancel, so we get, let me do it over here. Okay, so this is what we get. Now 9a, that is a is 3, so that is 27, and so these two cancel, and so we get 40 equals minus 4c, so we get that c is minus 10. Okay, so where are we? So we plug this in. No, we need still b. So what do we do to find b? We run out of good choices, and so now we choose anything that is left. So any remaining, anything, any choice is good. But of course, an easy choice, if you still can, is s equals 0. What do I mean, if you still can? What I mean is if you have not used it yet, because if you plug in a number you have used yet, you get exactly the same result, right? That's how mathematics works. Each time you do the same thing, you just start with the same input, your output is the same. So s equals 0. So if I plug in s equals 0, then I find that 64, that's on the left-hand side, and the right-hand side I get a times 3 squared plus 9, so that is 18a, plus 3b, plus c, minus 1. Okay, so a was 3, so that is 54, and c was negative 10, so this is minus 3b minus c, which is therefore plus 10, and so we find this is 64 minus 3b. All the 64's cancel, and I see actually that b is 0. Now that's also possible. Okay, it's not excluded that one of these is 0. Now, not both. Then there's something wrong. But one of them could be 0. Okay. So what does this mean now? So let's our function that we originally started with. Let me copy it. This one here. Okay. Let me clean it up a little bit, and then I can copy it better. So take this guy. Oops. Oh, why is it not giving me the copy option? Okay, so this one is now equal to a, what was a? A was 3. 3 over s minus 1 plus b times, but b was 0, s plus 3. So we don't have this s plus 3 here. But that's, you might say, oh, so it was wasted effort to do this. No, not at all. No, not at all. And then plus c, and c was negative 10. So minus 10 over s plus 3 squared plus 9. Okay. That's not still the, now we have to do the inverse Laplace. So the inverse Laplace. What is that? Well, this one, they have a 3 here. It's a single power, so it is actually 1 shifted by, so here a is 1, so e to the 1t. Okay, minus 10. Now what is this? We know that these guys are either sines or cosine. It's a sine if it's a constant, so in this case, if there would have been a b term, which happens to be 0, I just want to give you to see that this can happen, but in general it will be there, and that will be the cosine. Just keep that in mind. Okay, I realize I made a mistake here, right? Does anybody see the mistake in this one here? I made a mistake. I'm going to come back to it. So, so what do we do here? Okay, so in this one we know that it is the sine, so it is a sine minus 10, oh no, the minus 10 was from the sine here, sorry. Minus 10 times sine. But a couple of things now. First of all, is there a shift? Yes, negative 3 is the shift. And we also need to know what omega is. This is omega squared, so omega is, we always take the positive root, 3. So this is sine 3, and here we just put in t, and this minus e to the minus 3t accounts for the shift. And there's no cosine, so in general there would be a cosine, so there would be another term here, but this is the answer. Now coming back, I made a mistake because I was thinking about those formulas. What is the mistake I made here? So look at here. So reciprocals of 1 over a power corresponds to t to the power 1 less. But there is also an n factorial, which doesn't play in 0 and 1, because 0 factorial is 1, so as odd as it may sound, but that's something that makes our formulas work nice. 1 factorial is, of course, is 1, but there's a 2 factorial. So this to write this as 6t squared, that was wrong. I should have worded as 6t squared divided by 2. So what I mean to say is, we have that to t squared corresponds 2 factorial s cube. Okay, this is how Laplace transforms correspond. So 2 factorial is just 2. So we can, since Laplace transforms are linear, this means that we divide by 2 here, a half t squared will therefore correspond to 1 over s cubed. And so that's why we had to write a half here. Okay, and so of course it's cancelled, that would be just 3 then. Okay, but let me leave the 2 here to show you that I made a mistake. Well, luckily I found the mistake, right? I'm lucky, right, that I always find my mistakes. So sometimes you might think perhaps he does this on purpose. Okay, I must admit this one was not on purpose. Sometimes I do, but this one was not on purpose. And so if you missed it, yeah, it's a little thing that you miss, right? So this only plays when you have higher powers. So the first power and also even the square, it's not something that you happen to see. So it is kind of rare for us to use this, because most cases we have just simple roots like this, right? Okay, so that's the review. It is a bit of everything. There's still some other combinations that I didn't go over to, but I think this is, you're gonna get one of these types, something like this, okay?